This is Kevin Iga giving lectures on Math 250, Calculus 3. So today we're going to review for our upcoming midterm, midterm 4. Midterm 4 is on Tuesday and it covers a bunch of different topics starting from triple integrals, change of coordinates, then vector fields, then line integrals. We're talking about things about when is a vector field conservative, that's a big topic. Divergence, curl, and Laplacian, should know how to do those. And Green's theorem, which is occupied our time most recently. So let's review. Let's start with triple integrals here. Okay, so a triple integral, you need to know what a triple integral means. Like every integral, we are adding up a bunch of values of a function on something. So we break up a region in a three-dimensional region into lots of little boxes. We take a value of the function at each box, multiply it by the volume of that box, and you add it all up. That's the basic meaning of a triple integral. You should be able to compute it as an iterated integral. Okay, so turning into an integral of an integral of an integral. You should be able to change the order of integration. Okay, so I might give you an iterated integral. You need to write it as an integration in some other order. For instance, if it was dx, dy, dz, then you change it to say dy, dz, dx, or one of the other possibilities. You should be able to do a triple integral in spherical or cylindrical coordinates. Okay, putting in, of course, the extra factors of r or rho squared sine phi. And you should also know how it applies to mass, volume, average of a value of a function by mass or volume. Here we have an iterated integral. I've integrated x on the outside, then y in the middle, and then z inside here. Okay, sorry I didn't draw a picture of this. I should normally draw a picture. It's kind of hard to draw this on what I've got right now in a short amount of time. So I will just explain what this means. Notice that out here we have just numbers. That's how we always should have it. In here, the limits of integration are just a function of x. They could be numbers, but they could be functions of x. Here it's x because x is the variable outside here. And this integral only has functions of x and y. Those are the outer two variables here. The idea z is going to go from 0 to x, and this x squared plus y squared, this function of x and y. So while I'm doing this integral, I imagine x and y being fixed, and z is going to start from here and end here. So to describe roughly what this region is, x is going from 0 to 1, y is going from x to 2x. So just on those bases, you could just draw a two-dimensional picture here. It's kind of a triangle. X is going from 0 to 1, y is going to y equals x to y equals 2x. And you got a triangular region here in the xy plane. For every point in the xy plane, z is going to go from 0, in other words, the xy plane, up to this x squared plus y squared, which is this bowl-shaped object, this paraboloid. It's okay if you don't remember exactly what this graph looks like, but it's the idea is z is going to go from here to here. Okay. You might have problems where you have to change the order of integration. Instead of x on the outside, maybe x is on the inside or something, or in the middle. Of course, the only way to do this is to actually draw these pictures and reinterpret them as these iterated integrals. You should also, for that matter, be able to do these triple integrals. Okay, and let's see. Oh, and if you got this is Cartesian coordinates. If you got cylindrical coordinates, your dv should be r times dr d theta dz. Don't forget the r. And in spherical coordinates, don't forget the rho squared sine phi. This factor out in front. Okay, that's because of how the volume compares to what happens when you put these together. For applications, you should know that the volume is just the triple integral of 1. This should be very familiar to you with double integrals. We went over the same sort of idea, except that was area. This is volume. Mass, given by this, where rho is the density. This, of course, could be used not just for mass. If rho is charge density, then this would be the total charge for electrical charge. If rho was population density, this would be the total population. If rho is the density of some kind of concentration of some kind of pollutant, then this would be the total amount of pollutant. You're just adding up lots of little bits like this. More specifically, we're adding up little bits of rho dv. So rho is the small bit divided by the small amount of volume that we're talking about. And by multiplying by the small amount of volume of the small box, that's going to be a small amount of whatever pollutant or mass or whatever, and we're just going to add it all up. Averages of f. So if f is a function on 3 dimensions, then we can average it over this region. We can average it by volume or by mass. Averaging it by volume means we're just going to do this triple integral of f divided by the triple integral of 1. Okay, this is the volume. Okay, same way with mass, we just have to multiply f times the mass density here, where we also multiply this by the mass density here. So when rho is equal to 1, this turns into this formula here. So it's probably not needed to actually write all these things down. That this one could be viewed as this one, where rho is equal to 1. Of course, the denominator is now mass. Okay. The centroid and the center of mass are both averages of x, y, and z, and this one's by volume and this one's by mass. Okay. The x centroid is just the average value of x. I write x centroid. I mean, what the x component of the centroid. The centroid contains 3 components: x, y, and z, and you just average x, you average y, and you average z. Stick them into an ordered triple, and that will be the centroid. Same with center of mass. This is the average of x. Just put an x for f instead of f, and similarly here x instead of f for that. If you want the y coordinate, then you put y. If the z coordinate, you put z, and this way you get 3 numbers, giving you the coordinates for the centroid or the center of mass, depending on if we're averaging by volume or averaging by mass. So these are basically the same ideas as you had with double integrals. Nothing really new. Okay, next, change of variables and general coordinates. So whichever way you want to call this. If you have an integral on some region with x and y, and you'd rather use some other coordinate system, u and v, the idea is you've got some function, x is a function of u and v, y is a function of u and v. That's how you convert between u and v and x and y. And you can integrate over this other region. Okay, the regions are going to look different when you have these other coordinates. U is equal to something, v is equal to something, all the values of what u and v are equal to. And I have to multiply by this object here. Okay, and okay, there should really be an absolute value and a determinant here. So it's kind of hard to determine that that's what this means, but that's we're going to take a determinant and take the absolute value. Same with three-dimensional regions, except this is a three-dimensional Jacobian. The Jacobians are given by this, okay, in 2 dimensions and 3 dimensions, a 2 by 2 or 3 by 3 determinant. Okay. And one kind of change of coordinates that we actually played around with was the parallelogram. So if you have a parallelogram, okay, you just need to pick one of the points, call it P0, okay, and take these 2 displacement vectors, A and B. So it's this minus this, or this minus this. Those are my vectors A and B. And then we have x of u and v is P naught plus UA plus VB. This is the formula, of course, for parametrizing a plane, but the idea is the origin where u is equal to 0 and v is equal to 0 plugs in directly to get P naught. So 0, 0 will go to P naught. And then when u is 1 and v is 0, in other words, at 1 comma 0, this goes to P0 plus a, so it's going to go to that point here. And it's going to go in this linear fashion, so as it goes at constant speed here, then this is going to go at constant speed. And similarly, when I go to 0, 1, it's going to go out to here. Each of these lines here goes to lines where it goes to a little bit of b and then, however much of a. So in this way, we're going to get this parallelogram from this square, the unit square, for where u goes from 0 to 1, v goes from 0 to 1, using this change of coordinates. If you do this, of course, this is linear, so the derivatives are going to be constants, and so the Jacobian is going to be constant. All right, chapter 13, vector fields. There's not a lot to say about vector fields. You just plot in different points here and then into this, and it will give you some vector, and just sketch what vector they are at various places. So here's negative y comma x here. You notice when it's close to the origin, it's 0. When it's out here, it's much bigger, right? All right, next, line integrals. So there are 3 basic kinds of line integrals: integral of f ds, integral of p dx, also integral of something dy, or integral of the vector field dot dr. Okay. I didn't call this f here because I wanted you to remember that p dx and q dy can be combined to make a vector, a line integral of this type, f dot dr, where f is a vector field, where f is pi plus qj. Okay. So let's talk about each of these. Remember what this means. You're going to chop up a curve into lots of little segments. Okay, the C is the curve. And for each little segment, we're going to take the value of the function there times the length of that segment going from here to here. And if in the limit, when I get lots and lots and lots of subdivisions, that's going to get closer and closer to this integral here. Here's another integral. This is of the type integral of a function times dx. Okay. In this case, it's the same idea, except that I multiply the function times dx, which could be positive or negative. If it's positive if you go from left to right, it's negative if you go from right to left. It's basically the change of x at each point. Here's an integral of f dot dr. As I've said, I can rewrite it as an integral of p dx plus q dy, okay, and go back and forth. And integral of f dot dr means I take this vector field everywhere and take this curve, chop it into segments. For each segment, take the value of the vector field dotted with dr. Okay, so it actually all that matters with the dot product is the component of f in this tangential direction. And that's what this is going to be based on. If you have an integral on ds, those are the easiest ones to interpret. Okay. Length is the integral of 1 ds. If you actually look at how you compute these integrals, these line integrals, and you'll find that you get the formula for arc length that we did in chapter 10. Mass is the integral of rho ds. In this case, rho is the linear mass density, mass per length. You can average of a function by length like this, average of a function by mass, so multiplying by rho here and here. Okay. Again, the x component of the centroid and the x component of the center of mass, you just average x. You can average y, you can average z, and you get a triple that gives you a centroid for averaging by length, or a center of mass when you average by mass. Also, when I reverse the orientation, these integrals, the integrals with ds, do not change, but the integrals involving dx or dy do change with its opposite sign. Integral of f dot dr, also you get the negative of it when I change sign, when I change orientation. How do you compute it? Okay, so depending on which kind of line integral we have, integral of f ds, well, these kinds of things, the idea is, well, the idea with all these line integrals is you, instead of integrating it over the curve, you instead integrate it over t, where this is the parameterization of the curve. And t will start from some value, call it a, end at some value, call it b. And then we take the value of the function. Of course, the function is defined on the curve, but you can compose it with this. Just say what is x in terms of t, what is y in terms of t, and that'll tell you for each of these things what the actual value of f will be, times, it's mostly multiplied by ds, but I want to turn it into an integral on dt, so I have to write ds dt times dt to make it that. Ds dt is the length of r prime. So I just take the derivative of this, take the magnitude, stick it in there, and now I've got an integral on t, an ordinary definite integral. So that's how you do this one. You'll notice all of these, you just do the same idea. You turn it into an integral on t. I have to turn it, use the derivative here. So this would be ds dt, which is magnitude of r prime. This is just dx dt, which is just, you just take the x component of the parameterization and take the derivative. And here you have dr dt. Okay. And by the way, once I write it like this, I can rewrite it like this, and you can sort of see that that's capital T is the unit tangent vector. This divided by this length, and then you can see that you could write it down like this. These three are good ways to actually compute line integrals. This one's not a really great way to calculate this, but it's a good way to get an insight as to what this means. It's the extent to which f points along this curve. So in other words, I take f dotted with this unit tangent vector, and that's going to be the component of f that goes in the direction of t. In the example of f being wind velocity, this is sort of like how much the wind helps you in the journey. If it's going at your back, then this is going to be positive. If it's coming at your face, then this is going to be negative. The component of the wind that's going side to side is not at all being incorporated into this computation. And you just add it all up. If F is a force, it's kind of similar to this, except instead of wind velocity, you have some other force. And this is going to describe the work that it's going to help the particle move, or whatever object move along this path. And so these are interpretations of this kind of f dot dr. All right, the fundamental theorem of calculus for line integrals. Okay, so if I'm going to do an integral of f dot dr, and that f happens to be the gradient of a function. Okay, so this is like fundamental theorem of calculus, where you take the integral of a derivative. In this case, we're taking the line integral of the gradient. And we just take the value at the end minus the value at the start. So we can use this to compute line integrals if we know that the vector field is the gradient of a function. And if we know what the function is, you have to do that in order to actually do this computation. Then you can do this and not have to do any derivatives or integrals at all. This shows that it's independent of path. Okay? The integral of f dot dr is independent of the path as long as the vector field is the gradient of a function, if it's a conservative vector field. And what that means is it only depends on the starting and ending points. It doesn't matter which path you take, C1, C2, or this funny C3, they all end up at the same spot. Well, as long as they end up the same start and end at the same spot, it's just G at this minus G at that. Okay. How do you find G if this is a conservative vector field? Well, the idea is you take this, you integrate with respect to x, and instead of adding a constant, you add a function of y. So this is integrating, assuming y is a constant, this function. And then I take the partial derivative of this with respect to y, set it equal to this other one, and when I take the partial derivative of this with respect to y, you'll get something here. This will be h prime of y, okay, and is equal to this, and that'll tell me what h prime of y is equal to. Hopefully the result will be just a function of y. That it being that will be more or less what's needed for us to say that it's independent of path, and that is a gradient vector field. And you just integrate this to find h. Plug it back into this function to get whatever this is going to be. So here's an example. Here's a vector field. I just put together this vector field that happens to be conservative. Okay, and so we're going to need to find g. So partial of g with respect to x should be this. Partial derivative of g with respect to y should be this here. So you take this one, integrate with respect to x, holding y as a constant, and this becomes x cubed sine y. This becomes a sine of x, and then plus this arbitrary function of y instead of a constant. Then take the partial derivative of this with respect to y like this, x cubed cosine y, plus, and the derivative of this is 0, then plus h prime of y. And match it with this one, x cubed cosine y plus 5y to the fourth. So x cubed cosine y, x cubed cosine y, those cancel, and you have h prime equals 5y to the fourth. So h of y is y to the fifth plus a constant. Plug this back into this formula. This tells us what g is. A picture way of describing it is g is just given by this integral. Okay, what is it? Integral of p dx plus q dy, where c is a curve that goes from 0, 0 to the point xy. Obviously, you can change 0, 0 to another point, just as long as it's going to be the same point for whenever you do this, write this function. Okay. Change the point just changes this constant. And the point is, this has to be independent of path for this to make sense. Okay. If it's not independent of path, then this is not enough to say what this is, because I haven't told you what the curve is. If it's independent of path, though, then I can choose any curve and it'll do fine. And the idea is this integral here it shows that the partial derivative of this with respect to x really is p. This one shows that the partial derivative of g with respect to y is q. So the fact that these are equal is important for this to work. There's another thing that is that these things are independent of path if and only if these these integrals on these loops are 0. Okay, so here's the idea. Here's the start. Here's the end. Here's C1. Here's C2, and this integral is supposed to be equal to this integral. Okay, um, I can just move this to the other side of the equation and change the sign of this to negative. So this now goes from here to here. Okay, and this says that this integral plus this negative integral is 0. So this will equal this if and only if this is equal to 0. This is a loop here. So now this loop, the integral of that loop is 0. So the idea is if this is always independent of path here, then these loops always have integral 0. Conversely, if these loops always have integral 0, then I can walk backward in this argument to say that this is independent of path. So summarizing, here's what we got. All these different conditions, I've written it in the differential form, pdx plus qdy, but I've also written it as f.dr for the vector field form. And so this is what I just talked about. These two are equivalent. If you know this is true, then you know this is true, and vice versa. I've also said that the fundamental theorem of calculus for line integrals says that if you have a f is equal to the gradient of a function, then this is independent of path. The differential form of this is that pdx plus qdy is d of some g. This is the total derivative, if you remember correctly. Then there's also the Clairaut says that the p and q have to satisfy this. P sub y and q sub x have to be equal. Okay. We also said that if it's simply connected, then this will prove this. That's with Green's theorem. 3 dimensions works the same way. This argument is the same. This argument is the same. But this time we have p dx plus q dy plus r dz. And so we've got 3 conditions here. Okay. Qx equals py, rx equals pz, qz equals ry that Clairaut gives us. If you want, you can describe this as curl of f equals 0. We have not proved that this goes backward here in 3 dimensions. We only did that in 2 dimensions. But the proof that it goes back in 3 dimensions, if it's simply connected, will require things that we would have to talk about later. Div, curl, and Laplacian. Now that we're talking about curl here, it makes sense to talk about this. If I write f as pi plus qj, and if it's in 3 dimensions plus rk, so that's what the parentheses is. That is, in 3 dimensions, I'd have to have this as well. But in 2 dimensions, I wouldn't have this. Then div of f, divergence, is in del dot f is partial derivative of p with respect to x plus partial derivative of q with respect to y. And if it's 3-dimensional, plus partial derivative of r with respect to z. Notice that this is a scalar. So div of a vector field is a scalar field. Curl of f, this requires the f be 3-dimensional. It's del cross f. You get this 3×3 determinant. Okay, and scalar Laplacian is basically the div of the grad of a function is written this way. Is these second derivatives, not the pure ones, not the mixed ones. Partial derivative of g with respect to x twice, and then same with y, and then same with z if this is going to be a 3-dimensional version. Vector Laplacian, if you have a vector field, you just take the Laplacian of each component separately. These are the kinds of operations we talked about. Remember that you've got grad here, div here, curl here, and when you put some of them together, 2 of them happen to be 0, some of them happen not to be 0. This is the scalar Laplacian, for example. These other ones didn't have names, but when I subtract them, then you get the vector Laplacian. That's curl, curl, and then they do this div and then grad. All right, Green's theorem. So here's a region. It's got this boundary on it like this, and the boundary is oriented counterclockwise. And we assume that these partial derivatives are continuous on D, so in particular they exist. And then this integral of p dx plus q dy is equal on this curve here. It's an integral of f dot dr basically is equal to the integral on this region of qx minus py dA. Okay, so notice that this integral here ostensibly is about what's going on throughout this region, but this only looks at its boundary. It's kind of amazing that you get the same answer, and we don't actually have to look too closely as to what happens inside here to do this. because this only looks at this vector field on the boundary. So if qx equals py on this region, so that's the, I'm going back to this Clairaut result here. If this is true, why is this true? Well, this actually proves this. Okay, the integral of any closed loop of f dot dr is 0. And so if qx equals py, then this is 0 like this. Okay, you get 0. So this is Green's theorem. This is 0 then, if that's true. And then it gets 0. So that means this integral of f dot dr is always 0. As long as D doesn't have any holes in it. D is simply connected if every loop encloses only points in the region. Okay? There are no holes in the region. And if D is simply connected and f is defined on D with qx equals py, then f is conservative. So that's what we said earlier. This proves this, and now all of these are related on simply connected regions. The problem comes about when you have, you might have holes. So for example, this is the example I had, okay? And integral, so qx is equal to py, you could check, and this integral is positive. If I go around here, it's, you know, I'm adding a bunch of positive things, you're going to get something positive. So f is not conservative, and the point is f is not defined at 0, 0. So actually, one thing that's kind of helpful that I should have pointed out, if you look at this vector field here, this one is a different vector field. Okay, this one does not divide by x squared plus y squared here. They still point in the same direction, but they're different lengths. And you notice when you take the curl of this in 3 dimensions, so q sub x minus p sub y, I'm going to get a constant, in fact 2. And when I integrate around the loop, I'm going to get different amounts depending on what it is. But if I integrate around here, basically I'm going to get 2 times the area of the circle. Okay, that's what this Green's theorem would say. Yeah, if this is 2, then I'm going to get 2 times the area of this region. Okay, and the idea is if I am going along this vector field, let's say I go backward, then I'm going to get negative 2. So if I go backward, then the wind is always at my face. It feels like, the wind is conspiring against me the whole way, and indeed it is. But the only reason why that's so is because there's all this curl inside here. Everything inside here is going this way, and even out here, you might think, okay, oh, curl's here, but actually out here, curl is also non-zero because this one's going at a certain speed. This is going faster out here, and so in this little region here, it's kind of spinning around this way as well. It's going more this way than that way. Let's go back to this other example here. Here I'm rescaling it so that out here it's getting small, and inside here the vectors are big. And what I've done is at each of these places now the q sub x minus p sub y is 0. So kind of the curl around here is 0. So the idea is this is going at a certain speed, this is going at a certain speed, but there's more to go, but it's smaller vectors, and so those cancel out as it turns out, and there's like no curl out here. And there's no curl anywhere here except at the origin. All of so around here, clearly, the it's always f dot dr is always positive. Inside here with smaller regions, it's also the same value, and until I get smaller and smaller and smaller, I realize that the curl is not spread over evenly. It's all concentrated at the origin. And so the fact that this goes to infinity there, um, basically says that I've concentrated all the curl at one point. So the fact that Green's theorem, q sub x equals p sub y everywhere except on the point, right, at this point. But that point is important. When I integrate around this point here, I'm going to get, well, in this case, 2 pi. I just need to plug it in to compute it. Integral when I'm not surrounding this bad point by Green's theorem is going to be 0. But when I integrate some other thing that goes around this, I'm going to get whatever this one was. So this one of them I have to compute. Like this one I compute to be 2 pi. Then all the other ones that wrap around is going to give you the same thing. The reason is more or less this. So the integral of this, well, by Green's theorem on this shaded region here, if q sub x equals p sub y on this region, it doesn't work like at the origin, but I'm not including the origin. I'm just including this annulus. And then the integral, the double integral there, Green's theorem says I just look at this integral here, okay, plus this integral here, which I'm going to view as minus this integral here. So if I just reverse the sign of this to make it go counterclockwise, I see that this integral and this integral have the same value. So this C1 and C3 have the same integral if they're both going around the same way. If I go the opposite way, of course, it's going to be a negative. These are the different versions of Green's theorem. Okay, so this is integral p dx plus q dy is double integral qx minus py dA. This is the first version we saw. This is, of course, integral of f dot dr, which I can write like that, f dot dr. Actually, I've also written that f dot tds. Of course, that's the same as f dot dr. This one is, again, you have to view this two-dimensional thing as part of a three-dimensional vector field, and then curl makes sense, and I can look at the z component. Or you can just mean qx minus py. The point is this curl-like object, I'm integrating over the region, and we're going to get the same thing. If I switch q and p, put a minus sign on one of them, I get this one is equal to this. The point is now this becomes the divergence. And in return, this becomes f dot n ds, where n is an always outward-facing direction. And this is the idea. You add up lots of little, so this is the integral of f dot n, on the boundary of d, like this. It's how much things are flowing out of the region. And you can just add the divergence of each little part of the region. So break up the region to lots of subregions, and divergence of f is to what extent the vector fields are sort of diverging in that small region, how people are leaving, basically. And if I put them all together, then some of them that share a boundary, whatever goes out of one might go into the other. But on the ones on the boundary, that's what's left over. You get an integral of f dot n, where n is pointing outward, ds. All right, so those are the basic topics that we covered, and we are, well, I'm going to allow you time to ask questions between now and then. You can ask that over break. You can ask it in class on Monday. Monday, though, I am going to spend some time talking about surface integrals. So that's kind of like line integrals, but except instead of on curves, they're on parametric surfaces. So that's it, and good luck to everybody on midterm, and I'll see you on Monday.